Binomial experiment is defined. Okay, and these are the conditions that must be met to have something described as a binomial experiment. Now, some examples of binomial experiments would be flipping a coin or rolling a die a certain number of times. Okay. Now, in statistics, as interesting as those are, more interesting, if you will, from a practical point of view, is actually a voter preference poll. It's actually a binomial experiment. Okay? So basically when they do a poll, one candidate or maybe one side of an issue is called success, and the other one is called failure, although I don't think they use those terms probably. But they basically do an analysis or make use of these ideas when you do a voter poll. So if you have two candidates, all right, running for office, when you do a poll, in some sense what you can do is you can think of reaching into a great big barrel or urn or something of people, drawing them out and saying, okay, who are you going to vote for? All right? And then you put them back in the bowl, mix it up, and draw out another one. And if we define one of those candidates as success, all right, the other one as failure, again, in statistics, I don't mean in normative judgment. You might think of one candidate as being success and the other one as being failure, but that's not the intention here. So you count the number of successes, and what you've done is you've observed a binomial experiment, because what we do is we assume that all this big barrel of people is divided into either success or failure. And all I'm doing is I'm reaching in, pulling one out, noting what it is, put it back in, mix it up, draw it out on another one. Now, actually in polling, once you draw a person out and note their preference, you don't put it back in the bowl, so to speak. It turns out, because our bowls are big, or our urns are big, very big, and have lots of voters, the analysis doesn't really change. Okay, but we can think of it as putting the voter back in, mixing out, and drawing out another one. So it conforms exactly to a binomial experiment.
But if you don't put it back and you draw, you don't put it back, it will change your probability. Right?
It will, but the change will be so small.
Okay.
Yeah, you can actually do an analysis, but it turns out it's not going to be any different for practical purposes than what we do by assuming we put someone back in. Okay. All right. Now I've really done this slide overhead. The reason, what we do in the binomial experiment is we represent the number of successes, okay, or are interested in the number of successes. And if I use the letter X for that, all right, that would be a count of the number of successes in my n trials. X is a random variable. It will depend upon, every time I do this experiment, in general, I'll get different values of X. X can take on any value between 0 and n being the number of trials. The probabilities for the number, in other words, the probability of observing 0 successes or 1 success or 2 on up to 50 can actually be computed from these specific values and the fact that I have a certain number of trials and the probability of success in the given trial is a certain number. I'm going to show you how to compute that, in fact, or give you a formula for that. Now what we do is we kind of summarize all this by saying X has a binomial distribution. To be specific, I need to tell you how many trials I have and what is the probability of success in a given trial. Once I have those two, I can figure out the probabilities for X between 0 and n. All right. Now to figure out those probabilities, I need to introduce some terms here. The first one of which is what we call n factorial. You may have seen this idea before in your math classes. The exclamation symbol is the symbol we use for factorial in mathematics. So when you see a factorial, we mean something factorial. What do we mean when we say 1 factorial? Well, 1 factorial is 1. Okay? 2 factorial is 2 times 1. And nothing real special there. 3 factorial is 3 times 2 times 1. Now there's a pattern here. Here I start and end at 1. Here I start at 2 and end at 1. Here I start at 3 and end at 1. What is n factorial? By definition, we mean n times the next lower number, times the next lower number, and so forth, down 3, 2, and 1. So, for example, what is 7 factorial? Well, it's 7 times the next lower number, 6, times 5, times 4, times 3, times 2, times 1. Now you can stick this in and calculate it in your calculator. They often have this symbol or this a function or this process inside your calculator. I won't do it right for the moment. I'm more interested in the definitions. Okay, now, we also write down the following. 0 factorial is equal to 1. And that seems to be a break in the rules I had on the previous page. It turns out this is what we want to do. This is the most useful definition for 0 factorial. All right? You can think of it as just one of those odd cases where you just have to memorize. 0 factorial is equal to 1. There is method in this madness. It may seem mostly like it's madness, but there is method in it. Okay, now I've defined what I mean when I have n factorial. Now in this class, we can't talk about something about 7.5 factorial. 7.5 is not an integer, so we wouldn't ever talk about it. You go far enough in math, all the rules are broken. You can talk about 7.5 factorial, but we're not going to. Okay. That's the bad thing about math. You teach you all these rules, and then you get to a later class and say, oh, we're going to change the rules now. All right. Now, having defined n factorial, I want to define another symbol, which is written with the capital letter C. And on the left, lower left side, you have the letter N. And on the right side, you have the letter X. C stands for choose or combination. N represents, in this case over here, the number of trials. And X represents one of the values between 0 and n. This expression right here, we say verbally, this is n choose x. Okay, now, having given you a symbol, now I have to tell you what is the value of that symbol. In order to know that value, I need to know what n is and I need to know what x is. N choose x is by definition equal to, I take the number on the lower left-hand side, which I'm representing by n, and I take its factorial. That becomes the numerator. the denominator that is below the fractional bar, I have x factorial, which is this number in the lower right-hand corner, factorial. And then I multiply that times another factorial. Which factorial? I take this minus that, and minus that. I take that difference, and then I take its factorial. So, suppose I have the expression 50 choose 7. What does that equal? Well, I take 50 factorial in the numerator. 50 times 49 times 48 times 47. Things are getting way out of hand here. It seems that way. Now in the numerator I have 7 factorial. And then what I do is I have another factorial, which is 50 minus 7 factorial. So that's going to be 50 factorial, all divided by 7 factorial. Let's see, 50 minus 7 would be 43 factorial. Looks like a way big number. But we can do some simplifications here that will simplify our calculation. Okay. So the symbol n choose x is computed from this formula over here. To make things exciting in math, there are other ways of representing this symbol. You will sometimes see it written in this fashion where you have an n on top, an x on the bottom, and you have parentheses, but there's no fractional bar. We would express this verbally as saying the number of combinations of n things taken x at a time. If you say that often enough, then you figure out there's got to be a better way. So you say n choose x. Okay? So this is the symbol the author uses, but if you look at other textbooks or other sources, you might also see this here. It means the same thing. Okay, now, before we do this, how do we simplify this? Every time I do this, I remember the song, I don't know if you did this when we were kids, but when I was driving with my family, my parents said, we need to keep you kids busy, so we're going to go 99 bottles of beer on the wall. I don't know why we use beer, that doesn't seem quite appropriate for kids, but all right. What do we do in this case? How do we compute this? This is what happens here. This is 50 times 49. Let me write 50 times 49 times 48 and so forth. Down to, let's see, we'll eventually get to 43, and then we'll go 42, and so forth, and then we'll get down to 3, 2, and 1. Now 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. And then the other one is 43. Times 42 times 41 times 3 times 2 times 1. Well, guess what? All of these can be canceled. All those factors are the same. And so we would end up with 50 times 49 times 48 on down to 44 divided by this. And we can always do lots of simplification here. See, 2 times 5 is 10. That will cancel with 50 having a remainder of 5. This always turns out to be an integer, or a positive integer. Okay, there's never a fraction involved. Okay, so that's how we compute it. All right, now. Let me write down this formula here. Suppose I have this situation here. I'm rolling a die 50 times. I'm calling success, observing either a 3 or 6 in a given roll. What is the probability? What is the probability that the number of successes I observe is 7? So between 0 and 50, there's a 7 here. I could ask, what's the probability of getting 7 successes? That is equal to the following. 50 choose 7, the number I just computed up there. Oh, I didn't give you a final result, but that was, now, that's one number, and then what I do is I take the probability of success, which is 1/3. I take 1/3 and I multiply it or raise that to the 7th power, and then I take essentially, better system, but unfortunately if I move too far to the right, I think I'm going to be covering it up for some people here. So I take 1 minus the probability of success, which is actually my probability of failure, 2/3, and I raise that to the 50 minus 7 power. So this will be, this is going to be 50 times 49 and so forth down to 44, all divided by 7 times 6 times 5 down to 3, 2, and 1. That was the simplification of this. This would be 1/3 to the 7th power, and this will be 2/3 to the 43rd power. Again, those are kind of humdingers.
What?
Do you agree that 1 minus 1/3 is 2/3?
Yeah.
Do you agree that 50 minus 7 is 43?
Yeah.
So this can be simplified to that.
Yeah.
Back in the good old days, you see, we had to do this all by hand, and now we can just stick these numbers into a calculator and just like that get an answer. Well, actually, that's a little misleading. They actually used to produce tables for binomial random variables. They don't do that so much anymore because you can do this all in Excel. I'm going to show you how to do all the calculations in Excel. All right. So now.
Can I ask a question?
Yes.
How does the factor number that we did?
This thing
How
here.
How are you plugging that in? Yeah.
Well, remember, you see, this was 50 factorial
Okay.
over 7 factorial times 43 factorial. So when I was all done simplifying, it would be that there. See, I have nothing from 43 on down in the numerator because that canceled with a 43 factorial.
What is the px equals x, little x mean?
What is little p? Little p is the probability of success. This is what I've done here. I've used this formula. All I did is the following. I just used this formula, little x is equal to 7, n is equal to 50, p is equal to 1/3. So the probability that x is equal to 7 is equal to the 50, choose 7, times 1/3 to the 7th power, times 1 minus 1/3, that quantity raised to the n, that is 50 minus 7. It looks terrible.
Is that, so the factorial 50 divided by the factorial 7 is a really gigantic number?
Well, yeah, this number here looks to be very large, okay? Now, you can actually do enough cancellation. You see, I told you, see the 5 times the 2 is 10, so that 10 will divide into that. 7 goes into 49. So you will turn out, and it actually turns out to be an integer. You can do enough cancellation. Now you'd end up with multiplying several integers together, but on a calculator that's not so difficult anymore.
Yeah, so it's like 9988440. Is that what?
No, it has to be an integer.
What did you do?
No, I didn't do it, but it hasn't been. I don't do
Did you?
it. Hasn't been.
Oh,
Well,
I
let's-
didn't write decimal.
Yeah.
No,
Okay, it might, sometimes what will happen is your calculators will do a decimal approximation.
No, I didn't say decimal.
There are a couple ways of computing factorials.
I got
Uh,
884.
You got an integer, it's just really big.
It's really
Oh, yeah, that makes sense. Sure, sure. I don't know how to compute combinations directly in Excel. We don't actually need to do that. Let's see, let's do factorial. I think it does factorial. Okay, factorial. Let's do 7 factorial. 5,040. And let's see, we want to do, well here what we'll do here is the following. Let's do 50 factorial. So that's 3.04 and so forth times 10 to the 64th power, big number. Let's see, we also need 43 factorial. Another big number. And now N50 choose 7 is going to be this divided by the product of this and that. And that becomes, let's see, I guess that's what, 99,884,404, or 400.
That's what I got.
Okay, yeah.
I just didn't know if you were expecting a number, so tricky.
Oh, yeah, sorry. Yeah, these numbers get really large very quickly. So I'm going to show you how to do this and bypass all this factorial. I do want you to know the meaning of this formula here. I might give you some numbers, smaller numbers, and say, okay, what's the probability here? But as a general rule, what we're going to do is we're going to have Excel do the work, or you can have your calculator do the work.
And then is the answer that, or do we finish?
Oh, we have to finish by taking the result I had up there and multiplying times this.
Right.
Well, let's not do that. Let's have Excel do the work.
Okay.
Yeah. Yeah, it's gotten too easy for people these days. Actually, this, if we did this, I mean, what would happen is, you know, in the old days, I mean, they had tables. I don't know whether they went up to 50. And the tables are really cumbersome to use because, you see, P can be any number between 0 and 1. So there's no guarantee you're going to have a table associated with any specific value of P between 0 and 1. So what you do is you learn to use the tables and approximations of the table and so forth and so on. All right, let's take a look at, let's see, I want to create a new file again, or new, okay, now. So what I'm going to do here is the following. I think I'll make this a little bit bigger initially so we can see better. All right, so I'm going to do this example over here. I'm going to roll a die 50 times, so n is equal to 50. The probability of success is equal to 1 divided by 3, or 1/3. And let's see, I'm going to let x represent the number of successes. The smallest is 0, the next one is 1. Now, in this, I have a pattern, so I can select those two. I can move the cursor to the lower right-hand corner where it turns into a crosshair, and drag it all the way down until I get to 50. Whoops. A little too far. So I have the numbers 1 through 50. Now, so now I want to figure out the probability of that number of successes. This is how we do it. We use a function called binom, B-I-N-O-M. B-I-N-O-M dot, and then the one I want is D-I-S-T, binom.dist. Now the first argument in this function will be the number of successes I'm interested in. In the annotation, I guess this is probably not so clear, but it has number under S. That's the number of successes I'm interested in, and that will be in the cell to the left. All right, now, the next argument is described as trials. That's the number of trials, and that's 50. The next argument is probability under S. That's its symbol for P, the probability of success in a given trial, which is 1 divided by 3. Now the last argument we want to be false. This function does multiple things, and for our purposes what we want is we want to specify the last argument as false. Now, what is that? It's 1.568. E stands for scientific notation. 1.5 times 10 to the minus 9th. What's 10 to the minus 9th? It's a billionth. 10 to the minus 6 is a millionth. 10 to the minus 9 is a billionth. So this says basically the following. If I repeat this experiment, where I roll a die 50 times, and I count the number of successes, I repeat that a billion times, about 1.5 of those, I will get 0 successes out of the 1 billion times. And not very often. So if you were to roll a die and observe nothing but, or no successes at all, or excuse me, if you roll a die and you observe how do I want to say this? Suppose you, let me hold off until we get down to the bottom.
What was your false argument in that equation?
I'm sorry, what?
What was the false argument in that equation?
False.
Oh, you just put false?
Yeah, type in the word false.
Oh, okay.
So let me make this a little bit bigger here.
False, okay.
Yeah.
And it needs to be...
First argument references this cell, which is the number of successes I'm interested in. The next argument is the total number of trials in my experiment, which in this case is 50. The next argument is the probability of success in a given trial, which is 1/3. And the last argument needs to be false. Now, because of the way I set this up, I can now just extend this formula down, all the way down to the 50. All right. What's this number here? 1.392 times 10 to the minus 24th. Whew. I have no idea what the word is for that number. What this means is you have a die and it comes up either a 3 or a 6, 50 times in a row, and it looks like a normal die. Have I ever got a deal for you? You don't observe a result like that in this universe. You have to wait for a couple of billion universes to actually ever observe that. Very small probability. Okay? Now, what should the sum of all these probabilities be? I'm covering all possibilities, so the sum ought to be 1. Let's see if that's correct. It should be, there may be a slight round-off error that can happen, but, so what I'm going to do is I'm going to just drag my selection over all these, oops. The sum is 1. Now there can always be round-off errors because you're dropping, even a computer has some limitations in its calculation, but it should be close to 1. Now let's see if there are any more reasonable numbers. Oh, now we have some reasonable numbers. Let's see if we can figure out the largest number. The largest probabilities are associated with 16 and 17. In fact, they're the same. What this means here is the following. One way of thinking about it is that about 11% of the time when I do this experiment, I'll have 16 successes out of 50 trials. About 11% of the time, actually this would be about 12%, sorry. About 12% of the time I'll see a 16. About 12% of the time I'll see a 17. About 11% I'll see an 18. About 9% I'll see a 19 and so forth. Okay, now this has done all that combinations, all those n choose x, and probabilities raised to those powers. So the work has already been done for you. All right, and in creating a table like this, you want to use the function. Okay, I'm not sure I have any problems that actually ask you to do that, but typically we do this in software, it's just the computations are so involved. However, I want to emphasize, if I were to give you, say, maybe a 10, a 5, and a 1/2, you should be able to stick it into here and compute that probability. Okay, it shouldn't, I do want you to know how this formula works. All right. Now, if I have a random variable and it has a binomial distribution, what does that mean? It means I'm doing a binomial experiment and X represents the number of successes. So if I have such a random variable which has a binomial distribution and I have n trials and the probability of success is p. So I have to tell you what n is and what p is, but n can be 1 or 2, anything larger. P should be some number between 0 and 1, even though we could actually use both 0 and 1. They're just not very interesting. Random variables have an expected value. You can show, in this case, the expected value of X is nothing more than n times p. The number of trials times the probability of success. So, for example, in this case, it's going to be 50 over 3. And 50 over 3 is going to be, I guess that's going to be about 16. 16 and 2/3. Is that right? So 50 divided by 3 is, 16 and 2/3.
So is it just a coincidence?
No.
Okay.
No, it's not a coincidence that we had the maximum probabilities at 16 and 17. Okay. You would, that's often, I mean, that will be the case. I'd have to think. The fact that they're actually equal has to do with some symmetries involving n choose x. But, yeah, no, it's not an accident. What is the variance of x? N times p times 1 minus p. Now remember, we often represent the quantity 1 minus p by the letter q. So you might see n times p times q. What is the standard deviation of x? It's the square root of that quantity. All right. These are actually theorems in mathematics. They take a little effort to prove. We're just going to make use of those facts. All right. Well, I've illustrated this. Binomial probabilities may be easily computed using software. And I suspect if you look in your manuals for your calculator, they'll tell you how to compute these. Okay? I've never looked in here because I always use Excel, but I'm sure that TI-89 I know will compute this for you. All right, now, there's a really important approximation. And that approximation is as follows. Suppose I have a random variable and it has a binomial distribution. Think of this symbol as representing a table. Okay? In the case example I did up here, I had a table which had 51 rows. 0 and then a probability associated with that, 1 and a probability associated with that, all the way down to 50 in a probability. So we can think of that as a x and probability of x table. So this is kind of a shorthand notation for that. Now, let's assume that we have a situation where n times p is greater than or equal to 10, and n times q, or n times the quantity 1 minus p, is also bigger than 10. Turns out, this table here can be approximated by referencing a normal model. Which normal model? Where the mu is np, and the standard deviation, sigma, is the square root of n times p times q. Let's see it in action. What I have here, I guess I thought I had here. Oops. Suppose I have a binomial random variable where I have 30 trials and the probability of success in a given trial is 0.35. Now I could go through the process of creating a table, and what would happen is above the numbers 0 through 30, 0 to 30, I could figure out the probability of observing that number of successes. What I've done here is these rectangles here, the width, or these rectangles all have a width of 1. They're centered around the numbers 0 through 30, and the height is given by those probabilities in that table. This is what we call a probability histogram. Above each of the values 0 through 30, I've created a rectangle, which is the rectangles, in fact, indicate the probability of observing that value. So this height, above 10, this height here is in fact the probability of observing 10. So it's going to be, it looks to be a little bit over 0.15 in this case. Now, because the width of this rectangle is 1 and the height is the probability, 1 times the probability is just the probability. So that the area of this rectangle here is in fact equal to the probability of observing 10. Now I'm looking at this diagram, or this histogram, probability histogram. Note the following. The scales vertically are not the same as the scales horizontally. If I use the same scale vertically as I have horizontally, you couldn't see these rectangles. They'd be too small. So what I've done is I've magnified it so as to better see in the vertical direction. Okay. So this here, all right, one way of thinking about it is, well, I can create a table from 0 to 30, figure out the probabilities, and then create this, what we call a probability histogram, where I create rectangles whose areas turn out to be the probability of those values. All right, now, on the previous page, I said this can be approximated by a normal model. Which model? I take this times that, and I get 10.5. And I take this times that times 1 minus that, so that's going to be 0.65. And then I take the square root of all that, and I end up with a 2.61. Now, if I graph the bell-shaped curve associated with a normal model, where this is the center and that's the standard deviation, it looks like this blue thing right here.
But this, the top of the table is now the 2.61.
Okay, if you take the square root of 30 times 0.35 times this, you'll end up with 2.61, or approximately.
It doesn't match your graph.
Why does it not match my graph?
You see
The peak here
P is
directly over
10.5.
10.5.
But the Y
If this is centered at 10 and this is centered at 11, what's halfway in between here?
I know, but how about the Y?
The Y is not, this here tells us how spread out or how compressed it is.
Okay. Okay.
Believe me, this is correct.
No, I believe you. I just.
All right. So it's a very famous result. It's a version of what we call the central limit theorem. I think the guy, I think it was either Laplace or Lagrange, some French mathematicians about 200 years ago, maybe some others who kind of found this result, and they've kind of amplified it. This is a special case of what we call the central limit theorem. In what's the famous theorem in geometry? Pythagorean theorem. What's the famous theorem in probability and statistics? Central limit theorem. Okay? This is a version of the central limit theorem. Now, it's all very well that I have a probability histogram, all these rectangles, and I have a bell-shaped curve that seems to follow the general pattern here. Let's make use of that fact. Okay? This is the way we're going to do it. We'll see how this is useful. So I'm going to assume we're considering this case. I have a random variable x, and it has a binomial distribution, all right, where I have 30 trials, and the probability of success is 0.35. So basically I'm saying n is equal to 30, and p is equal to 0.35. The mean value of this random variable is just my 10.5, and my standard deviation of my random variable is equal to approximately 2.61, the 2 decimal places. So all I'm doing over here is copying the relevant information here. Now suppose I want to know what is the probability that I observe a value, say, between 8, right here, and let's say 11. Well, let's see. What I mean by that is the probability that x is equal to 8 plus the probability that x is equal to 9 plus the probability that x is equal to 10 plus the probability that x is equal to 11. That's what we mean when we see a symbol like this here. Let's go back to Excel and let's compute that. Let's see. About that. So what I'm going to do is I'm going to go to a new sheet here so I don't have to create a new file. And let's make this big here. So what I'm doing is I'm considering the case where I have n equal to 35 and the probability of success is equal to 0.35. And what I'm going to do is I'm just going to focus on what is 4 values of x. It'll be 8, 9, 10, and 11. So, and I'm going to figure out the probabilities of those values using my function. Okay, now, so I have 4 probabilities. It's fairly easy to compute these using the binomial function. It wouldn't be too hard to do this by hand, but it would be a little tedious. And the other thing is, pretty easy to make a mistake if you do it by hand, unless you've had some practice. There's a hint. Okay. I don't say do lots of calculations, do a few, all right, involving probabilities so that you have some facility with that. Okay, now, what is the function that we want to compute? Well, it's the binomial, and it's binomial.dist, or binom.dist. Now, the first argument, I'll refer to this cell here. To separate arguments, I put down a comma. The next argument is the number of trials, so that's 35.
0.35
0.35.
I'm doing, the overhead was 35, so 35 trials. The probability of success I'm using is 0.35. And then the last argument is false.
Do they always choose false?
Yes, in this, yeah, for computing these probabilities, if you do true, you get what's called a cumulative probability. So if I put true here, what it would give me would be the probability of 8, and 7, and 6, and 5, all the way down to 0. And that's sometimes what you want, but I think it's easiest to focus this way.
The overhead is 30.
The overhead is 30?
Yeah.
You would say that. All right, let's go back to 30. Sorry. We want to do that. I want to... So this is 30 here. All right. So I think I've got that right now. Sorry. Yeah, and I've got it over there. All right. Now all I'm going to do here is I'm going to extend this formula down. All right. And then what I'm going to do is I'm going to sum all of these. All right, now basically what this is saying is the following. This probability is equal to about 53%. I'll put it down 53106. All right. Now, let's go back to the overheads. And make use of this. Now, what I want to do is I want to make this a little bit bigger here. Now, I claim here the following. That sum over there is the sum of this rectangle right here. Plus this rectangle right here. All right, plus this one here. Plus the last one here, so that's okay. The sum of all these rectangles is equal to 5.3106. Now, we're going to make use of this approximation. And the way we're going to do it is the following. First of all, the blue line is associated with our normal model, where the center is at 10.5 and the standard deviation is 2.61. Now, if we think of this rectangle, which is the correct interpretation, as being centered at 8, what is the left-hand side? Well, it's halfway between 7 and 8. So it'd be 7.5. So this right here we think of that as being 7.5. What about this over here?
11.5.
That's halfway between the 11 and 12, and so that's going to be 11.5. Now let's focus on the normal model. So I'm going to just basically redraw, but on a different scale, a bell-shaped curve. The peak is above 10.5. And I'm going to indicate 7.5, that's going to be about right here, say. And then 11.5 is going to be about right here. This area here should be about the same as this portion right here. I'm using a different scale, but this is intended to be that right there. Can I figure this area out here in another way? We convert both the values, 7.5 and 11.5 into z values. And then what we do is we make use of our table in the back of the book. So let's figure out the z value associated with 7.5. So the z value is equal to 7.5 minus the center, 10.5, all divided by 2.61. And if we do that computation, all right, we're going to get the following. 7.5 minus 10.5. I actually don't, I should be, that's a -3, and then I divide that by 2.61, and that turns out to be, I'll round it to 2 decimal places, so that's going to be a negative 1.5, excuse me, 1.15. Now the other one, the other z value, is equal to, that's going to be 11.5 minus 10.5, all divided by 2.61, and that difference is 1. So basically all I need to do is take 1 and divide it by 2.61. And that turns out to be the 2 decimal places, 0.38. So right, this is 0.38.
Why
Okay.
you got a 2.61? Oh, that's a. Okay,
Yeah, that's the
a-
standard deviation for our normal model.
Okay.
Okay, now, let's look, if we look at our table associated with the standard normal model in the back of the book, we look at the position associated with 0.38, that will be the area to the left of that. And if we do so, when I get back to my table, the entry I have there is the following. It's 0.6480. Okay, so 0.64, did I say 80? All right, now. Oops, I want that here, sorry, 0.6480. Now what's the entry in the table associated with the negative 1.15?
0.4443.
Okay, yeah.
I'm just kidding.
No, it's actually
0.1.
0.1251.
Yeah.
0.1521. Now, so this area here, which would be the same as the following area, would be equal to 0.6480 minus 0.1521. And if we do that on our calculator, Whoops, I didn't do that right. We got something wrong here.
This should be, first the Z should be positive.
Let me make,
2.
I need to get an answer very close to what I have there.
Is that first the Z score should be positive 2, should be 10.5 minus 7.5. And the area, because you go out shift to the left.
Hold on here. Let me do my calculations. I'll get back to you, okay?
Oops. It's negative.
Ah, I know what I did. I switched the 5 and a 2. It should be a 2 and a 5. At 60 years old, I've discovered, or actually a little bit beyond that, I've discovered I'm a little dyslexic. Well, actually, it's pretty easy to make a mistake to be made. So I have 0.648 minus 0.1251, and I come out with the following. 0.529. That's pretty close to that value right there. All right, now, when we get to polling, we have values of n equal to 1,000 or 500, and there's almost no difference at all. Okay, it's just the differences are so small. All right, now what I've done here is I've illustrated what I mean when I say a binomial distribution can be approximated by a normal model. If I'm going to do that, I need to know which normal model. In general, you take n times p, that becomes your first argument for n, and then you take the square root of n times p times the quantity 1 minus p, or what we also know as q. That way we come up with a normal model. We know the center, we know the standard deviation. We can determine probabilities associated with this by converting to z values and using our table. Okay.
I got it.
Okay. All right. Now, we don't discuss the Poisson or exponential probability models in this class, even though you'll find them in chapter 7, or you might find them in chapter 17 if you have a regular text. I think they may be pulled out of the ECC special edition, if I'm not mistaken. Sometimes in the special editions they pull out sections. I don't know if they have done that for these two ideas, but I don't cover them in this class. Okay. I think what I'll do here for these slides, what I'm going to do is I'm going to ignore them for this week. And what I want to do is I want to move on to talking about chapter 18. And the reason I want to do that is because we're going to actually apply these ideas very quickly now to polling. All right? And we'll pick up here and review this next time. But let's start this process and make use of these ideas. Okay. 18 is described as sampling, distribution. I guess that shouldn't be a plural. I don't think so. Models. Now, first thing we need to do here is to change slightly how we look at, for example, polling or observing a number of results in a binomial experiment. What we do is, rather than looking at the number of successes, we look at the proportion of successes. When you get a poll, what do they tell you? They tell you a percentage, and then they give you a margin of error. So typically, they might say something like the following: a certain candidate had 52%, and then they'll say the margin of error is maybe 3%. Something like that. We're going to see where those ideas come from, or at least in kind of a broad form. Now, so they don't tell you, when they give you a poll, they don't tell you, well, they'll probably usually tell you, or sometimes they'll say, well, we polled 1,000 people. And they'll give you then a percentage of individuals supporting a given candidate or a given proposition here in Oregon. So they really don't give you what X is, the number of successes. They give you the proportion of successes. Now what we do is we use the symbol P with a hat above it to represent the number of successes, all right, divided by the number of observations. P hat is a random variable too. This is one of the cases where we kind of break the idea that a random variable is represented by a capital letter. Actually, this is used sometimes to represent the random variable and sometimes to represent the exact observed value. So there can be a little misleading. But for the moment, I'm going to let P hat be the random variable, which is the number of successes divided by the number of tries. In this case over here, I would take the number of successes, which could start at 0 and go on up to 30, and I divide it by 30. So P hat can take on values between 0 and 1 in increments, if you will, of 1 over 30. See, I'm going from 0 to 30. So this goes from 0 to 30. This is 30. So in going from one value, 0 over n, or 0 over 30, to 1 over 30, I'm incrementing by 1/30. So this is a random variable. It takes on values between 0 and 1, and in general in increments of 1 over n. Now anytime I say I have a random variable, we should ask, oh, do we know what its mean is? And do we know what its variance is? And do we know what its standard deviation is? The expected value of P hat, this random variable, which can be represented either in this notation or this notation here, is nothing more than our value of P. Was that the case? I'm defining P hat to be the number of successes divided by the number of trials. This can be written as 0 plus 1 over n times x. In my rules that I stated previously, this is my value of A, and this is my value of B. So the mean, the expected value of P hat, if you refer back to the rules, is 0 plus 1 over n times the expected value of x, or the mean value of x. and I said the mean value of x is n times p. These two n's cancel, and then that result is p. So I use the rule, sorry, I run out of space here. So what I have is I have a random variable which has a binomial distribution. And I'm looking at a new random variable, which is the random variable x divided by n, which can be thought of as 0 plus 1 over n times x. This fits the rule, the pattern I was describing previously, where 0 is my a and b is 1 over n. The rule says the expected value of p hat, which is the same thing as the mean value of p hat, is 0 plus 1 over n times the expected value or the mean value of x. Well, I stated previously there's a theorem in mathematics that says if I have a binomial random variable, the mean is simply the product of these two values. This n and that n cancel, and I end up with p. The random variable p hat has as its center, if you will, just the value of p. Using the same rules for variance, the variance of p hat is p times q. Remember, q is the quantity 1 minus p. P times q over n. And the standard deviation is nothing more than the square root of that.
So the difference is just the n was not here, then an n is here.
Well, remember in the case, let's go over here. For the random variable x, the mean value is n times p. The variance of x is n times p times q, which is also n times p times the quantity 1 minus p. When I get done applying the rules, all right, that I stated earlier today in class, all the simplifications end up by saying the variance of p hat turns out to be p times q over n. And therefore the standard deviation of p hat is the square root of that quantity. All right, now, p hat is the sample proportion of successes. We go out and sample from our population. We observe a certain number of successes. We divide that by the number of observations I make. That's what we call p hat. Polling results are reported as proportions or percents, and not as successes out of the sample size. Again, we could use binomial probabilities and distributions to find out probabilities associated with p hat. There's no reason to do that because we have a good approximating model. When n times p is greater than or equal to 10 and n times q is greater than or equal to 10, p hat may be approximated by a normal model where the center is at p, at the standard deviation, the square root of p times q over n. Basically, I'm making use of the fact that a binomial distribution can be approximated by a normal model. And what I'm doing is I'm basically adjusting that for looking at p hat, which by definition is the number of successes x divided by n. So what we often do is the following. In a poll, we think of the observed value of p hat as an observation from this normal model. In general, we don't know what p is, but we're going to make use of our knowledge of this, if you will, to come up with what's called the margin of error. Okay, now, let's see how this plays out. Let's see, where am I? This, I think we'll do it up here. This is the kind of the mental model that we're using in Poland. We have a population, and in this population we have a whole bunch of successes, a whole bunch of failures. P is the number of successes divided by the population size. Q is the number of failures divided by the population size. Now, I usually don't know those numbers. In fact, that's why we do polling, is because we don't know, we don't often know exactly the size of the population. Usually we have a pretty good idea of the size. But we certainly, as a rule, don't know the number of successes in the entire population, and we don't know the number of failures. Now, assuming the population is real big, again, what we do when we do a poll is we reach in, grab someone out, and we say, okay, are you a success or are you a failure? Well, we don't ask it that way. People hang up the phone when... But that's, in effect, that's what we do. And what we do is we observe P hat. Now, if the probability of success, little p, is fixed, and that's what we assume, then P hat can be thought of as an observation from a normal model where the center is at P and the standard deviation is at, or the standard deviation is P times Q over N. So what in effect I have done is the following. The horizontal, all right, represents possible observations of P hat. I go out and I observe something. I actually take the number of successes divided by the number of trials, and I have what I call an observed value of P hat. Now, in general, I don't know if it's bigger than the value of P or less. But this, because of the way in which I'm doing the sampling, I'm reaching and blindly pulling someone out and noting whether it's success or failure, all right? So I'm going to do this n times. In a poll, typically it's somewhere between 500 and say 1,500. I think a typical value is about 1,000. Now I'm assuming that in this population there is an identifiable or precise number of successes. All right, and I take that and I divide by the total sample size, or population size. That's what I call my Q. Now I don't know what Q is, but I'm assuming, or excuse me, I don't know what this little p is, the probability of success is, but I'm assuming there is such a number. Now, in real life, political preferences will change over time. But the closer you get to election, they tend to firm up, okay? So this is, I think, a reasonable model to try to assess how people are feeling about either a given candidate or a given proposition. Now, having described this sampling, we can think of p hat, the actual proportion of successes, as being an observation from a normal model which is centered at p and has this standard deviation. Now, if I knew what p is, I wouldn't do the poll. This value is the value that is reported here. Where does this margin of error come from? Well, this is what we do. The standard deviation of p hat is exactly equal to the square root of p times q over n. Now, if I knew what p and q are, the whole point of a poll would not be very meaningful. But what I can do is now I can use my knowledge of the value I just observed, p hat, as an approximation of p. So this is going to be approximately equal to p hat times 1 minus p hat, all divided by n. And this also can be written as square root of p hat times q hat, where q hat is, again, is by definition that difference. And this is what we call the standard error of p hat. So when I talk about a standard error of p hat, I'm computing it from these formulas here, which I think should be a pretty good estimation of the standard deviation of p hat, the exact value. Now, suppose, again, looking at this model, I don't know in general whether p hat is above p or less than p. But I do know the following. Let's use as an example this value right here, which I'm going to define to be p, the center, plus 1.96 times the standard deviation, which is p times q over n. I'll explain why I use this here. I'm going to label this as p minus 1.96 times the square root of p times q over n. I need to make this a little bit further here. And maybe make this a little bit further over here to be more realistic. Okay, now, the significance of the 1.96 is the following. For a normal model, if I take these values and convert it into z values, the z values are going to be 1.96 and then negative 1.96. This area here is 95%. Okay, now, the value of p hat that I observe will lie between this value and this value here about 95% of the time. Again, the dilemma here is I really don't know what this is, but I do have an estimation of it. Now let's take this observation. And again, I don't know whether this is bigger than p or less than p. But think of the following: as I observe a value, and then I can go to the right a certain amount and a left a certain amount, there's a pretty good chance that if I take this value and multiply it by 1.96, I'm going to get values on the right and the left. There's a good chance, even though I don't know exactly where I am, that the range that I've determined by taking this and adding and subtracting the margin of error will contain the true value of P. You can almost kind of think of it like an aircraft that's landing on an aircraft carrier. Most of the time they're going to catch that wire. And so I don't know whether I'm, in general, my value here is to the right of P or to the left, but if I go out from that 1.5 times an estimate of that, there's a good chance that the resulting range, which is computed by taking the center value and adding the margin of error, and taking the center value and subtracting the margin of error, because this right here, this quantity,
Why you choose 1.96?
because this is 95%. Let's hold on that for a moment. What we call the margin of error is computed by taking a special value of Z. The special value in this case is 1.96 times the standard error of P hat. This quantity here is an estimate of this times the standard deviation. And if I take my center value and go to the right, that margin of error, and to the left, that range of values are likely to include in it the true value of P. There's a 95% chance, roughly, that that will be the case. Now, why 1.96? Well, there are a couple of reasons. 1.96 has the property that if I start at the center and go to the right, 1.96 times the standard deviation, and go to the left, this area is 95%. Why 95%? Well, why not? We actually we could make other choices. When they tell you this margin of error, what they're actually telling you, or what they're not telling you, is that this is what we call the 95%, it's called the confidence level. They're not telling you that. Why don't they tell you that? Look, I've spent now 8 weeks or something like that getting to this point. You've diligently, most of you have diligently been paying attention, or at least trying to, especially when an exam is coming up. And we're just now struggling to get to these ideas. If you said 95% in a paper, or actually if you said 95% over the air, you just lost 99.99999% of your listeners right off the bat. Because even if they took this class, they have long forgotten it. And if they haven't forgotten it, they've shoved it into a corner of their mind, never to be assessed again, or accessed again. Well, the thing is, this is the way in which polling is done. They typically use a 95% confidence level. It's not the best choice, but it's not a terrible choice either. And what is important is they use the same procedure from poll to poll. Now,
they always use these 95%.
I believe so. Now, there may be...
always 1.96. I thought this cannot be over 1. It's 100%.
Well, the area can never be over 1. The area here is 95%. That has nothing to do with the 1.96.
Okay, explain again 1.96.
1.96 is a Z value. And if you look in the area between negative 1.96 and a positive 1.96, if you use the table, you'll find the area between those is 95%. If you convert those back into values associated with this normal model, it will be this number and that number there.
Okay.
All right? So what we're doing here is the following. We're coming up with an observed value of p hat. We're saying we can estimate this quantity, which we don't know. The estimate is called this. We take this estimate and multiply it times by a special value z. The value z is determined, if you will, by the confidence level we want to use. Typically it's 95%. It doesn't have to be that, just kind of a cultural norm. I take that and I multiply it times that. That's what we call the margin of error. And basically what we're saying when we see a report that 52% support a given candidate and the margin of error is 3%, they're saying we're 95% confident that the true value is between this plus that and this minus that. So it would be between 49 and 55%. The best thing I do in this class is disillusion everyone as to the certainty of statistics. In a real poll, you know, you could have, there's a 95% confidence. The value could be as low as 49% or as high as 55%. So if we were talking about a proposition, could well be the proposition goes down. Now there are some other reasons why these are not bad choices. When we're talking about candidates, typically we report the highest percentage amongst all the candidates, and everyone else is lumped together into other category. So even if this were, say, you could get less than 49%. If someone, towards the end of a campaign, has a poll and reports this, and the other candidate may be on the order of 45% and so forth. The thing is, what's going to happen is this is still a reasonable prediction as to who's going to win, because there are often many candidates, there are third-party candidates, which will tend to drain away from both of these. But in such a way that if the report is 52% towards the end of an election, that's a pretty good indication, or there's a fairly high probability that that person will in fact win the election. But it is not certain. Now, all politicians, or at least their advisors, I would never accuse politicians of being this smart, but their advisors usually are. They already know this. And this is why, for example, why politicians, parties, and so forth go to great efforts to get their voters out to the poll, so as a way of just inching in enough, far enough, so that their candidate wins. Okay? Well, I think we better declare victory on this discussion of polls before I have a complete rebellion and the instructor is overthrown and the dictatorship of the students is established. So remember, exam is on chapters 8 through 16. We'll spend a half hour addressing questions at the beginning of the class. We'll spend 2 hours on the exam, and then we'll pick up after that on this topic here.
You didn't talk about the 52% or 3% at all in this.
Right, that's just a particular case.
Okay.
That's a particular value of p hat. In general, I don't know what the value p is, but I'm going to use this information, and I described how they would use this information as a kind of range of estimates as to what the value p is.
I'm confused.
I usually use capital letters to represent events. I don't mind, but I just want you to be consistent.
Okay, so
Okay,
And then you were saying these are independent.
well,
Shouldn't it
No.
only be independent if B is completely contained in A?
no,